So okay, let's start. This is lecture 9. Cool. Yeah. So in the last couple of classes, we were looking at the LPTV systems, and even in the circuits that we had seen earlier, the main issue we saw was frequency translation. That is, frequency at input either getting translated to some other frequency at the output, or multiple frequencies at the input, they all falling back to one particular frequency at the output, right? So in this class we will look at a technique called the N-path principle that actually helps us to reduce the effects of this frequency translation to some extent. And one possible way to arrive at this technique is to make the following observation. Say you have an LPTV system that is varying periodically at a frequency Fs. Okay. So now let us say at the input I apply a tone at a frequency F. Now at the output, what frequency components can I expect? F plus KFS, right? So I might have a tone at F. I'll have, say, okay, shift it up. Okay, fine, let's do it. Yeah, so let's say this is F plus Fs, say F plus 2Fs, F plus 3Fs, F plus 4Fs. Similarly, on the other side, you will have tones at these frequencies. Right. So what is the harmonic transfer function that governs this frequency translation? H0 of F, right? So I'll just write it as H0, and of course this is H1, H2, H3 and H4. Similarly you have H minus 1, minus 2, minus 3 and minus 4. Okay. So now let us say, let me first copy this. Okay. So now let us say I have another LPTV system, but that is now varying periodically at a frequency 3 times Fs. Okay. So now let us say I apply a tone at a frequency F. What frequencies do I expect at the output? Right, it will be F plus K times 3Fs. So obviously I will not have this translation happening. Similarly, there will be nothing at 2Fs and also at 4Fs. Similarly at this side also. Oops. Right? And please remember, even the inverse is valid. That is, if these many frequencies are the input, they can also translate to a frequency F at the output, right? So this is, it goes either ways, right? So now we can clearly see the number of frequency translations that is happening has reduced by factor 3. Okay. So the observation we make is, at say if we increase Fs, the number of frequency translations that reduces. Okay, but of course we might not be actually able to increase Fs because of multiple reasons. One, probably because we might not be able to design circuits operating at higher Fs, or second, which is more important, the Fs might dictate some other parameter in your system, right? For example, in the bandpass filter that we have seen, what was the frequency Fs determining? It was basically determining the center frequency of the bandpass filter, right? So it might not be feasible to increase Fs directly. Okay. So all we need to do is to take LPTV system or say systems which are at Fs, that we can't change, but to the outside world we make it appear like it is periodically varying at 3 times Fs. At least in words it sort of makes sense to some extent, right? And to see how we can do this, let's look at the following example. Say I have a signal x1 of t. Okay, so let us say it is a periodic signal which is periodic with a time period ts. Okay, so basically this x1 of t is a proxy for your impulse response of an LPTV system. Okay, so I'm just writing it as another signal so that you will come out of the framework of impulse response and treat it as any normal signal, right? And similarly, let us say we have two other signals, x2 and x3. Both are again periodic with the same frequency, right? And again, these two are impulse responses of some LPTV system. Let us say I form another signal x hat of t, which is x1 plus x2 plus x3. What can you say about this signal x hat of t? That will also be periodic with ts, right? So basically x hat of t minus ts, this x hat of t. But what we want is, we want the overall signal to be periodic at a higher frequency. Okay, so let us say we choose that frequency to be 3 times Fs. So all we want is x hat of t to be periodic with a time period of what? Ts by 3, right? So we want to see if we can actually enforce this. Okay, so probably I'll move to another page. So this is what we want. And what is x hat of t minus ts by 3? It is x1 of t minus ts by 3 plus x2 of t minus ts by 3 plus x3 of t minus ts by 3. We want this to be equal to x hat of t, which is basically x1 of t, x2 of t, x3 of t. Okay, so basically this is this guy and this is this. Okay. So can you stare at this equation and tell me if it is possible to enforce this equality, or under what conditions? Yeah, I think you got it, right? See, one trivial solution to this obviously is to make each of these equal, but that simply says that each of these signals is periodic with ts by 3, which means the periodic frequency is 3 times Fs, right? And that's not what we want. We still want individual signals to be periodic with ts, but the sum needs to be periodic with 3 times Fs. So, okay, so did everyone get what his solution was? Okay, you just look at the equation.
They will be out of phase by 2 pi.
Which one?
x1, x2, x3.
Right.
So then only this.
Okay. So I mean, the simplest way to think is, see, I will just replace these by say this is x2, x3, and x1. I rewritten the same thing, right? So if I equate these 3 fellows, then I can do it, right? And of course, we can just confirm if there is some contradiction in this. So what I say is x2 of t is x1 of t minus ts by 3 x3 of t is x2 of t minus ts by 3, and x1 of t is, okay. So of course first is simple, we just make x2 to be a shifted version of x1. The second equation simply says x3 is a shifted version of x2, which means this is x1 of t minus 2ts by 3. So here we already have a relation between x3 and x1. So of course this must also satisfy it. Only then we have a consistent solution, else there's a contradiction. So we already know x3 in terms of x1. So what is it? x1 of, x3 is x1 of t minus 2ts by 3. This is, right, so this is basically 3ts by 3, which is ts. And we know x1 is periodic with ts, so this is equal. Okay. So if we enforce this condition where x2 and x3 are time shifted versions of x2 of x1, then the sum is periodic with 3 times fs, right? So that's what we have to do. We have to take x1. The second signal must be shifted version of x1, and the time shift is ts by 3, and x3 of t is x1 shifted by 2ts by 3. Okay. And as I mentioned, each of these signals are proxies for the impulse response of an LPTV system, right? So all I have to do is to get an effective impulse response h hat of t. Okay, so let us say x1 is some h of t comma tau. So I need to get a system whose impulse response is h of t comma tau plus, what should be the second term? T minus ts by 3 comma tau Is it clear? Okay. So I'll have to basically I have to realize this overall system as sum of 3 other systems, and the impulse response of the 3 systems are basically staggered in time by ts by 3. Okay, is it clear? And of course we can take an LPTV system that is varying periodically at fs, and I'll say that gives the impulse response h of t comma tau, right? That's our base LPTV system. Okay. Now how do I get these two fellows? So the question is, I have one LPTV system that has an impulse response h of t comma tau. Okay. Now what we have told is we need to get another system whose impulse response is shifted in time by ts by 3. You can't control the time at which you are applying the impulse, right? Input is coming, isn't it? Sorry? Yeah, where should we delay? What should we delay? Yeah, I mean, that is, you're saying in words, but I have the system, right? See, this is the same LPTV system, okay, like, same LPTV.
Impulse should be shifted by.
Yeah, but like I mentioned, you don't have control over the time at which input is coming, right? The same input, see, what this says, I have x of t that goes to h hat of t comma tau and comes out. This is what we are realizing as h of t comma tau, h of t minus ts by 3 comma tau, h of t minus 2ts by 3 comma tau, and we are adding, right?
All the three branches of t comma tau, they are delays in those branches. So
Yeah.
the input is delayed.
No, you should not delay the input as such. The impulse response is what is getting delayed. Okay. See, in words, what it says, this is basically the impulse response of an LPTV system that is varying periodically. The second one is the impulse response of a system that is also varying periodically, but the time variation in that circuit is shifted by Ts by 3. Is that fine? So what I am trying to say is, everything that is varying periodically in time in that network, if I make sure they are all shifted in time by Ts by 3, then we will have this. For example, one example is, let us say there is some resistance R, okay, inside this network that varies periodically in time. Okay, so what we will do, we will shift the time variance by T0.
Just like changing the pulse from -20 to 1 visual solution.
Exactly. See, in the systems that we have been looking at, the time variance have been coming because we have periodically operated switches. Okay. So in our example specifically, like I was mentioning, we have control signals to the clock phi 1 of t. What we have to do? We'll just delay the clock.
Just like interleaving.
Yeah, kind of. Exactly. That's exactly interleaving. Yeah. Right. So if you do this, this will have an impulse response of what? Ht minus t naught comma tau. Is that fine? So just by delaying the clocks that are given to our system, we delay the response of the system to an impulse, right? And that is basically delaying our impulse response also. Fine?
You are saying delaying the inputs is not trivial and as delaying the clocks.
Clocks are just clocks, isn't it? See, input can be a continuously varying signal. Okay. See, if you have x of t, if you have to ideally delay it as x of t minus t, let's say t naught, you need to have something like this, right? And getting this response for all frequencies is not possible. Whereas delaying clocks is straightforward. Okay, so let's build our system so that it appears like an overall system, periodic at 3fs. So what I'll do, I'll take x of t. I will have the base system operating at fs, and let's say the controls to the clock is phi 1 of t. So now I'll have the same copy, and here what should be the delay? Ts by 3, and this is simply 2Ts by 3. Okay, and the same input we will feed to all these fellows, and the output is basically summed, and you have. Okay. So this is called a 3-path system. Okay, and now let us say I apply an input at a frequency f. What frequency components I'll observe at pi of t? It will be f plus k times 3fs. Okay, so basically this entire block if you look at the effective impulse response, that will be periodic at a frequency 3fs. But the important thing to note is each individual LPTV system we have here they are all still periodic at Fs. Okay. So if you observe each individual node voltage in each of these systems without applying an input, you will find that these voltages are still periodic at Fs. Okay. By doing this sort of combination, we are mimicking periodicity at 3Fs. But the individual voltages here in each of these systems, they will still be periodic at Fs only. Okay. Great. So now you don't have to stop with 3, you can extend it to n, and that's pretty straightforward. So let me draw that also. For n-path, we'll take the first system. Let us say this is clocked at phi 1 of t. So the second will be delayed by Ts by n, and the last will be delayed by n minus 1 Ts by n. Fine. And of course the same input you give to all the systems, and you sum all the outputs. And again, if you feed a sinusoid at a frequency f, you will have tone set f plus k times nfs, and vice versa. If you have, what frequency components can fall back to f plus k times nfs. Only frequencies at these values, they can fold back to a frequency f at the output. Is it clear? Okay. So now let's take a 3-path system, for example. Say this is a 3-path LPTV, where each individual LPTV system is varying at Fs. Okay. And as we saw, if you feed in a sinusoid at f, the frequency components you get will be f plus k times 3Fs. So what can you say about the harmonic transfer function h1 of j2 pi f? 0, right? Because what frequency translation this governs? Input is at f, output is at f plus fs. Okay. And similarly, even h2 of j2 pi f, that will also be 0. Okay. So for this 3-path LPTV system, where each individual LPTV is periodic at Fs, the harmonic transfer functions that could be non-zero or will be of this form: h3l of j2 pi f, right? Where L belongs to integer. So this could be non-zero, that's all. All other harmonic transfer functions will be definitely 0. Okay. And similarly for the n-path case, only the harmonic transfer functions h0, h plus or minus n and so on, only they will be non-zero, and rest all other harmonic transfer functions will be 0. Okay. So now we looked at how we have this behavior in time domain. So let's actually look at the same in frequency domain and confirm that indeed these harmonic transfer functions are 0. Okay. And for that, first let's look at a single LPTV operating at Fs. Now if I look at the time varying frequency response for this LPTV and then take the Fourier series coefficients, what will I get? That is the harmonic transfer function, right? So this is hk of j2 pi f. Okay. So now let us say the same LPTV system is delayed by T0. Okay. So what can you say about the time varying frequency response? No, the time varying frequency response. See here what it says, T minus T0, everything is delayed in time. Okay, so for the impulse we saw the response is delayed by T0. Similarly for the sines exponentials also, the response will be delayed by T0. Okay. So for this fellow it will be J 2 pi f comma T minus T0. Is that clear? So now if I take the Fourier series coefficients for this fellow, what will I get? Right? So it's just a delay. So we'll have a corresponding phase shift, which is e power minus j 2 pi k fs times T0. Is it fine? Kth harmonic transfer function, so the frequency is kfs, the delay is T0. Yeah, so if we have the same LPTV system which is delayed in time by T0, for the harmonic transfer functions we just have a phase shift angle. Okay, so let's actually quickly compute how the harmonic transfer functions look for the LPTV, that is the original network and the delayed LPTV. So for k equal to 0, for the original, for the network without any delay, what is the harmonic transfer function? Simply h0 of j 2 pi f. For the delayed network, it is same. Okay. So this makes sense because the zeroth harmonic transfer function is basically the DC or the average of the signal. If you delay the signal, the DC will not change. Straightforward. Now let us look at k equal to 1. Here you will have h1 of j 2 pi f. What will we have here? h1 of j 2 pi f times e power minus j 2 pi k times fs. K is 1, so fs times T0. And similarly for k equal to 2, the second harmonic transfer function, that will have a phase shift of 4 pi fs T0. Okay. So of course this phase shift also makes sense because say I plot h of j 2 pi f comma t for some frequency, say f equal to some f1. So versus time, say the response looks like this, something. Okay. So let's say this is 0, this is Ts. Okay. Now when I shift it by a time T0, so what will happen? The same response gets shifted by some time. Okay, so this is no longer okay. Now let us say you find the fundamental frequency component for this, that is h1 of j 2 pi f, right? The strength of the sinusoid at fs in this signal is the first harmonic transfer function. So let us say that something like this. Okay, so here the same sinusoid will be delayed, right? And if you have twice the frequency, the delay will be this. The delay is same, so the phase will be. The phase will be 2 times. Right? Frequency times the delay. Frequency is doubling, the phase doubles. Okay. So with this information, let us try to calculate the harmonic transfer functions for the 3-part system. and we obtain the response for the three-part system by taking our base LPTV system. We'll add the response of this to the same LPTV system delayed by Ts by 3 plus one more delayed by 2 Ts by 3. Okay. Okay. So let's find for k equal to 0. Yeah. For k equal to 0, the original network, the harmonic transfer function was h 0 of j2 pi f. Even if you delay it by Ts by 3, the 0th harmonic transfer function is same. And for the third system, it is same. So in total, you have 3 times the 0th harmonic transfer function. So now let us take k as 1. For the undelayed network, it is h1 of j2 pi f. Now for the system where we have a delay of Ts by 3, what will we have? Times e power minus j2 pi k times fs, k is 1, fs times the delay, which is Ts by 3, and Ts is 1 over fs, so these two get cancelled, 2 pi by 3. So now what will be the case for the third system? h1 of j2 pi f e power 4 pi by 3. So now if you sum up all of these, we have 0, right? Because we have h1 of j2 pi f plus you are adding 3 equally spaced complex exponential, so this will be 0. So for k equal to 2, this will be h2 of j2 pi f. Hey. Okay. Yeah, so for the system where the delay is Ts by 3, what will we have? h2 of j2 pi f times e power minus j2 pi k times fs, so we have 2 fs times the delay Ts by 3, so this is 4 pi by 3, this 4 pi by 3 plus h2 of j2 pi f, here it will be 8 pi by 3, and see 8 pi by 3 is same as 2 pi by 3, right? It's 2 pi plus 2 pi by 3, right? So I'll write it as 2 pi by 3. So now even if you sum all these 3, that will also be 0. Now for k equal to 3, we have h3 of j2 pi f. Here I will have the same, but what will be the delay? 6 pi by 3, that's 1, and here we have 12 pi by 3 or whatever, again that's 1, so we have the same. So we have 3 times h3 of j2 pi f, right? And we can generalize it for n-part system, only h0, n to 1 will be non-zero, and the overall harmonic transfer function will be n times the harmonic transfer function for the original LPTV network. Is that fine? Great. So now if you look at it, the way we have made these harmonic transfer function to be 0, it relies on 2 important things. One is the fact that we had the same h1 in all the 3 systems, right? So which means that the 3 systems are indeed identical except for the delay, But of course, in practice, there is no two quantities that is exactly identical. So there will be some mismatch among the systems. Okay. So in practice, you will be limited by the mismatch, right? And this cancellation also depends on one other thing. What is that? Sorry? Time shifts, right? This became 0 because this was 2 pi by 3 and 4 pi by 3. And this was possible because the time shifts were exactly Ts by 3 and 2 Ts by 3. So in practice, if there is some delay in these shifts, it will exactly not cancel again, right? And also delays in clock phases. Okay. And if these two exist, the harmonic transfer functions, they will not be 0 exactly, but they will be a small quantity, right? So in presence of these, for the three-part system, let's say the h k of j2 pi f, where k not equal to 3 times n, this ideally would have been 0, but in presence of mismatch, this will be a small number. Fine. So this is the principle behind this N-path operation, where you take one LPTV network, that's your original network. You see that you have a lot of frequency translations. So to minimize the effect or to reduce the effect, you have n copies of the same network. Just the impulse response is delayed by Ts by n or whatever. And in our systems, it is straightforward. We just need to delay the clocks by the corresponding time delays. And then you add up all the outputs. And then you will see that frequency translations will be only from multiples of n times fs. Okay. So now that we have this tool in our toolbox, let us try to use this and improve the circuits that we were looking earlier. And the first circuit that we looked, what was it? What was the first LPTV circuit that we came across? The buck converter, right? So let's quickly recap that. The circuit was this. So we had the input from the battery, I'll call V in. That was given to two switches like this. So let's say this is on for a duty cycle D and this is phi 2. We filtered it using an LC filter and that's it. And here you will have the load current. So if the input is V in, a DC input, what will be the average output? It's D times V in. And what was the problem that we saw here? The output, although it's approximately equal to D times V in, if you actually sketch the waveform, see this is the D times V in, so it will be hovering around this, something like this, right? It will not be a sinusoid, but something like this. Okay. So in this buck converter, what are the harmonic transfer functions that you want to be non-zero? Or taking a step back, what is the frequency that you have applied to the circuit? Huh? DC, 0, right? So what is the harmonic transfer function that you want to be non-zero in the circuit? H0. Input DC, we want the output to be constant DC. So we only want H0 of J2 pi 0 to be non-zero. And all the other HK, we want it to be 0 in principle, right? And of course, what is the frequency at which the output is having this ripple? If let us say the clocks have a frequency Fs, right? So if you look at the spectrum, you will have a DC, Fs, 2Fs and so on. We only want the DC component. Fine? Why do you want infinite? Okay, let's come to that. Yeah. Okay, so first before trying to see how we can use the N-path principle here, let's sketch the current waveforms so that you'll have a better understanding. So, great. And to plot the waveforms, we had actually assumed that the output is approximately constant, right? We didn't consider the ripple, we assumed the output was constant and then we calculated. And in your assignment, you would have found the ripple will be maximum at some duty cycle, and what was it? Half, right? So we'll take that example. So D is half. So V out is approximately Vn by 2. Okay. And yeah, let's sketch the waveforms. So we know that the inductor current is 1 by L integral dl of t dt, where I will define the current in this direction and the voltage with this polarity. Now when phi 1 is on, what is the inductor voltage VL? Vn minus Vn by 2, so that's Vn by 2. So the inductor current, what will it do? It will ramp up, right? Input is, the inductor voltage is constant, the current will ramp, and what is the slope? Vn by 2L. Okay, so it will do something like this. And when phi 2 is on, what is the inductor voltage? Minus Vn by 2, right? Because this is 0 and this is Vn by 2. So the inductor current will ramp down with the same slope. And if the average load current that we are drawing is I load, what can you say about the average inductor current? That will be same, right? Because in steady state, there cannot be any average current flowing in or out of the capacitor, because we know this voltage is constant, right? Or it doesn't blow up to infinity. Okay, so let's quickly sketch the inductor current. So this is time and this is inductor current, and let us say okay, yeah. So let's say till this point phi 1 is on and phi 2 is on in this part. Okay, we know that the inductor has an average current of I load. So let's say this is that. During phi 1, the current ramps up. So it does something like this. And when phi 2 is on, the current ramps down. Right? So these two values will be equal. Okay. Fine. Now this is the inductor current. The capacitor current will be what? It's just the inductor current minus the average. So this variation in the current that will flow through the capacitor, and that's what is causing the ripple voltage. Okay. So if you think about it, the real culprit here is the inductor current, because the inductor current has this ripple. The same ripple current without the average is flowing through the capacitor, and that's what is disturbing the output voltage. Is that point clear? Okay. So now if we use the N-path principle, what we'll try to do is we'll treat the inductor current as the output quantity, and we'll try to make sure that the inductor current has minimum ripple. Is that fine? Great. And when you use this multiple paths and do this buck converter, so it is called multi-phase buck converter. Okay. Because they have to give separate name. And the circuit is again simple. We take the original circuit. Let me draw it. This is the original circuit. Let me call the clock phases phi 1 of t, phi 2 of t. And let's say this is VL1, IL1. And let's say take two paths, right? I'll have one more copy. So what should I change for the two path operation in the second circuit? Basically, see, thing to notice, the clock phases must be delayed by Ts by 2. Okay, yeah, pi phase, but in time it's Ts by 2, right? Of course, in this case, phi 1, phi 2 is this time shifted version, so I'll simply drop this time and I'll call this to be phi 2 and this to be phi 1. Okay, that is true only in this case. Okay, and let me call this inductor voltage as VL2, the current to be IL2. Now we have two copies of the same LPTV network. The same input is given, right? The same input is given, and we have to sum up the output quantity. And we saw that the output we should be focusing on is the inductor current. So how do we add the two inductor currents? Sorry, we have two currents. How do you add them? Say this is a current I1, I have a current I2. Sorry? Basically you just connect these two, right? And then here it will be I1 plus I2. That's all. So here what do we do? Yeah, basically we'll connect these two together. That's all. Right? Copy and mark it. We'll connect it like this. Okay. So let me redraw it and reduce clutter. So the same input is given to the original network clocked with phi 1, phi 2, and we have the inductor. Here I have phi 2, phi 1, more inductor, and I have to sum up these two, right? And once I do it, here you see the two capacitors come in parallel, so I will replace it by a single capacitor. So let's say it is some cap, and now you see that this two-phase buck converter can provide twice the amount of load current, right? Because these two currents come in parallel, so it's equivalent to single current source of 2 times I load. But let us say I am interested in delivering only a current of I load, because the load is same, right? The load is drawing I load. Then what can you say about the average current, right? I load by 2. So IL1 average is I load by 2. IL2 average is also I load by 2, right? So basically each branch needs to only provide half the current that is demanded by the load. Okay, and that will make sense because if you look at it, each inductor is connected to the output for 1/2 the time. Okay, and now these are the two inductor currents we have. We have tried to sum them up by making them flow through one node. So this is the total current, IL total. Okay, so let's sketch the waveforms of these currents and see what happens. Okay, and as usual, first let's look at the inductor voltages so that we can draw the currents. Say when phi 1 is on, what is VL1? V in by 2. Okay, VL1 is V in by 2. So which means IL1 ramps up, and the slope as usual is V in by 2L. What happens to VL2? Minus V in by 2. Right? Because when phi 1 is on, this switch is grounded, this voltage is still V in by 2. So you have minus V in by 2. So what can you say about the current IL2? That will ramp down with the same slope. So now when phi 2 is on, what do you expect? The roles will simply interchange, right? That's all. So let me just copy paste it. So here VL1 will be minus V in by 2. So the current will ramp down for the first inductor. VL2 will be plus V in by 2. So this will be okay. So now let's try to sketch the waveforms again. Connected it here. Okay, let's put the waveform. This is the time, and I'm plotting the total current. And we know that the average currents for both the inductors is I load by 2, right? So first let me mark that I load by 2, and again let's say this is till this point it is phi 1 is on, and here phi 2 is on. Okay, and in phi 1, yeah, the first inductor current ramps up to do something, and in phi 2 it will ramp down. Okay, so I mean it doesn't look identical, but it should be. Now for IL2, the opposite happens. So it will ramp down, and here it will ramp up. So now if you add the two, what happens? It will be constant and equal to I load, right? So this will be the this is I load, and this is our total inductor current. So now you see that the overall current that is actually flowing into the capacitor, yeah, it is, this current is I load. So the current flowing through the capacitor is 0. So the voltage is virtually constant. Okay. So now we have 0 ripple in VL. Fine. Okay. And the case we considered is for a 2-path or a 2-phase buck converter, and duty cycle was half, right? And this had 0 ripple. Similarly, if you go for a 4-phase, you can find that for duty cycle of 1/4 or multiples of 1/4, say 1/2 and 3/2, 3/4, these will have 0 ripples actually. Okay, and let us say if you take a 2-phase buck converter, but your duty cycle was 1/4, you will notice that the ripple will not completely get cancelled, right? But of course it will be smaller, right? That's what you expect from the N-path operation, right? So ripple will be smaller, that is, ripple amplitude is small, right? And say now you have an N-phase buck converter where I don't satisfy this condition for 0 ripple. Again the same, ripple amplitude will be smaller, but what can you say about the frequency in the ripple voltage? NF is see, N-phase buck converter is basically our N-path LPTV system, right? See, this N-phase is basically your N-path LPTV, right? And you are giving an input of 0. So at the output, the only frequency components you could expect is 0, NFS and so on. So the fundamental frequency for the ripple will be at NFS. So the amplitude reduces, the ripple frequency increases. Is that okay? And in your assignment again, I don't know if you plotted it. Say you plot for a single phase buck converter, the normal buck converter. If you try to plot the ripple amplitude, that is the peak to peak ripple, as a function of duty cycle, what would you get? It was a parabola, right? It was d times 1 minus d sort of thing. So you had something like this, and you had a maxima at half. Okay. Now say you do a two-path operation. So this is just one phase. If I do a two-phase operation, where all I will get zeros? I will definitely have a 0 at half, right? And of course at these two extremes it will be 0, right? See, what does duty cycle of 0 mean? The switch is not even, right? V in is 0, sorry, V out is 0. So don't expect anything. The switch is open and the switch is closed, done. And when D is 1, this is always connected. So there is no switching again, we expect constant. So when you have a two-phase operation, you will have 0 ripples at these 3 points. Okay. And this is for two-phase. And again, if you go for a 4-phase, you will have 0 ripples at all these points. Right? And you can see as you increase the number of phase, the peak to peak ripple will also reduce. And that's simply because we have eliminated many of the harmonic transfer functions in the LPTV system. Okay. Okay, so let's stop here and we can continue.